So another important part of sets that will help us do counting later on is understanding the idea of union and intersection. So unions are taking everything together in the two sets and putting them in one big pile. But you got to remember that items are not repeated in sets. You never list things twice. And then the intersection represents what they share. So again, you can see by the definitions, the first definition in set builder notation, X is in the union of A and B if X is an element of A or X is an element of B. And X is in the intersection of A and B if X is in both sets, A and B. Just like the Venn diagrams were helpful to use for the other ideas with sets, they're helpful here too. So we'll assume that A and B have some kind of overlap. We'll talk about what it means if they don't. So here's my universal set, and we'll say here's A, and maybe it shares some elements with B. Here's B. So A, here's B. The union is everything together. So in this particular case, the union is all of the stuff in A, but also all the stuff in B. So all of this information here would represent the union. Whereas the intersection is only what is shared. So for the intersection, here's my universal set. Here's my A, here's my B. The intersection, again, only what is shared, so only the overlap of the two sets. So in this case, it'd be just that little piece. By the way, with observation here, you should be able to notice that A union B contains the intersection. So the intersection is inside of the union. Right? So you can see this piece is inside of that piece. Just a quick observation there. So you should be able to look at two sets and decide what their union or intersection will be, because later on, if we see that we have a union or intersection, it will determine how we count the elements of those sets. Here's an example to kind of run through the definition and the ideas. So we have our universal set, the whole numbers 1 through 9. That's what those dots mean. We're just continuing the pattern. R is 1, 2, 3, 4. S is 1, 3, 5, 7. So it looks like most of the odd numbers, or all the odd numbers except for 9. And then T is 2, 4. So we want to find each of these sets. So the first one is R union S. That's everything together in R together with everything in S, but you don't repeat elements. So 1's in both, so I'll list 1 once. 2 is only in R, but all you have to be is in one of them. 3's in both. 4's in the first one, 5's in the second, and 7's in the second. So I basically put everything together in one basket, but I don't write down any repeats. So R union T will be the same thing. So 1's in R, so it gets in the union. 2 is in both, so it's in the union. 3's in R, so it's in the union. And 4 is in R, so it's in the union. It's actually in both. Now this is interesting. Notice R union T equals R. What's going on here? Well, R contains T. Actually, if you look here, these two pieces are actually T. So in other words, T is actually a proper subset of R. So that means when I go to do a union, I'm just going to end up with R. Because remember the picture. So here's my universal set. Here's R. Here's T. So if I go try to do what's all together, I get all of R. That's what's happening there. Now the intersection is going to do something interesting for the same reason. R intersect T would be only what's shared, and the only thing shared is 2 and 4. And again, that's equal to T, and it's because of this property here, because they happen to have a containment property. That won't always be true. It's only true because T is contained in R. Okay, now finally T, remember this means complement. So for part D, T complement intersect R. So everything in the universal set not in T intersect with R. What I'm going to do first is figure out what T a complement is. T complement would be everything in the universal set except for 2 and 4. So it'd be 1, not 2, 3, not 4, 5, 6, 7, 8, 9. And then we want to intersect that with 1, 2, 3, 4. So only what they share will be in the intersection. So they share 1 and 3, it looks like. And that's it. So this intersection is 1 and 3. I just put a mark on that one since there's work. I want to make sure I mark the answer. So you can see it's all about understanding the definition. And again, some sets you can naturally think of as unions or intersections, and that will help us with our counting problems. Now, I did mention before that there's some cases where the sets don't overlap. If they don't overlap, what we have are disjoint sets. So I'll give you an example of these types of sets. So let's say A is 1, 2. We'll use a real simple example. And B is 3, 4. Clearly, they don't share anything, right? So A intersect B is empty. It's the empty set. Whenever that happens, that implies automatically that A and B are disjoint. So sometimes this will happen, and if it does, we want to know because it affects how we count. And remember, that's the ultimate goal. So before, we didn't have any that we did that were disjoint, but this might come up, so we should make note of it. So I also want to show you how to deal with finding unions and intersections when the sets are simply described instead of definitions. So this is one example of that. It says, okay, the universal set's all whole numbers. And A is the set of all even numbers smaller than 20, and B is the set of all even numbers larger than 15. Find the intersection and the unions. Okay. So we got basically all whole numbers as universal set, and so that includes negative numbers. I'm going to draw a picture to understand these sets. So A, all even numbers less than 20. So that includes some negative numbers also, right? So even numbers less than 20. So that would start at 18, and that would count down. So we got 16, 14, ... 0 is technically an even number, ... minus 14, etc. Okay, and then B, set of all even numbers larger than 15. So even numbers larger than 15, that would start at 16, right? So this goes from here, starts at 16, that's the first element of the set if you were to put it in order, counts up, so it goes 18, and forever. So let's just put a big one up there so we remember, So even numbers larger than 15. Okay, we want to think about the intersections and the unions. So A intersect B, it's what they share. So A intersect B, I want to see if I can essentially write it down. In other words, can I write a nice, compact either list, or can I use set builder notation? So I see that they definitely share 16. So because remember, it's even numbers less than 20. Do they share more than that? Well, remember, I wrote this kind of weird. Maybe I should start like this. 18 is actually the first element, right? Because if I was to put this in order by definition going this way, less than 20, the first even number less than 20 is 18. So 18 is in this set, 16 is in this set. 16 and 18 are also in this set. But this right here is the biggest number in this set, and this is the smallest number in this set. So the intersection must be 16 and 18. Okay, what about the union? So union's what you get when you throw everything together. It looks to me like you actually get all even numbers, period. Think about this. This goes on forever. It's all even numbers less than 20. So this goes all the way to minus infinity. And then this is all even numbers larger than 16, and we know they overlap. So in other words, we've covered every possible even number. So this is actually the set of all x, such that x is even. Very interesting. So it's a interesting pair of sets because of the way they overlap and how many numbers they cover. So you should be comfortable doing problems such as this, where you got to think about it a little bit, but it also shows you how powerful this notation is, because these sets are hard to describe, but look at how simply we're able to describe the intersection and the union.